You have now learned how to get the global importance of a feature for a model. In this lesson, you will learn how you can get the importance of a feature on a particular individual's prediction. With methods like the permutation method, we have seen that we can get the importance of each feature to a model overall. But let's say we care not about understanding a model overall, but understanding a single prediction of a model on a patient. We want to know how important the blood pressure was for the prediction of the model on patient A. This particular patient has a blood pressure which is very high, so we might expect that although age is in general more important, on this particular patient, their blood pressure would be driving their risk. So we can train a model to predict the outcome Y using age and blood pressure, and once this model is trained, it comes back with a prediction of risk of 0.93 for an event. And we're going to represent this model with F and BP and age as the inputs. Similarly, we can also train a model to predict the outcome Y using just the blood pressure and using just the age. And these two models can also make predictions of the risk. Notice that the prediction using the BP is similar to the prediction made by the full model, but the prediction made with just age is much smaller. We can compute the importance of a feature for patient A by taking the difference in outputs with and without a feature. So for age, we have the full model minus the model output that doesn't contain age, and that difference is negative 0.01. Now when we remove BP, the model output changes by 0.55. Thus, the importance of BP is much higher for this patient than the importance of age. Notice that this is very similar to the drop column method we have seen, except we're looking at the output of the model F, not the performance of the models. However, this method can fail to recognize important features when there are correlated features. Here's an example of that. Let's say that instead of using one blood pressure value for the patient in the model, we use both the systolic and the diastolic blood pressures. These record the pressure in the blood vessels when the heart is beating and resting respectively. They're highly correlated, and for this patient, both very high. So like before, we should expect that the importance of both of these features should be very high. Instead, here's what happens. Like before, we look at the risk prediction of a model that uses all features as input for this patient. We also look at the risk prediction of the three models, which don't include the age, the systolic blood pressure, and the diastolic blood pressure features. Notice this time, at least one of the two blood pressure measurements is always in the feature set, so we always see a high prediction of risk. Using our method, we find that the importance of each of the features is hence very small, and we're not able to recognize the importance of the high SBP and the high DBP for this patient, even though the setup is almost otherwise identical as when we had one blood pressure measurement. Let's see how we can fix this.